Good morning, students. Let us start a new chapter, group theory. So, in this chapter, we know about the some important concepts. So, in that, binary operations. We already studied in 12th standard. What is binary operation? We know about the binary operation. If S is any non-empty set, then star is said to be binary operation on set S. If for all AB belongs to set S, then the unique element A star B is belongs to set S. Thus, star is a binary operation on set S. That is, for all A comma B belongs to set S, this implies that A star B is belongs to S and A star B is here unique. And also we know about the some important notes. So in that, about binary operations. In that first one, the symbol addition, multiplication and dot etc. are the denoted for the binary operation. And the second one is a binary operation can also be defined as a function, that is a function is said to be g cross g tends to z. Then we go for third one, addition and multiplication are the binary operation on rational numbers. Binary operation on rational numbers. Then fourth one is addition, multiplication and subtraction are the binary operations on integers, rational numbers and real numbers and complex numbers. But division is not a binary operations on these all. It means again integer, rational numbers, real numbers and complex numbers. Now we know about the definition of groups. A non-empty set G with the binary operation star is said to be a group if it is satisfied the following axioms. If it is satisfied the following axioms. In that first one, closure law, that is for all A comma B belongs to Z, then A star B is belongs to a set G. And second one, associative law, for all A B C belongs to a set G, then A star bracket of B star C is equal to bracket of A star B star C. Then third one is law of identity or existence of identity. For all A comma B, then the exist identity element E is belongs to G such that A star E is equal to E star A is equal to A, existence of identity element. Then fourth one is law of inverse or existence of inverse. For all A comma B is belongs to a set G such that an element A inverse is belongs to G such that A star A inverse is equal to A inverse A star is equal to E only. Now we go for the next concept, that is abelian group or commutative group. A group G comma star is said to be an abelian group if it is satisfy the commutative law. When we say the abelian group, it satisfies the commutative law, that is A star B is equal to B star A for all A comma B is belongs to a group G. The next one, definition is semi-group. When we call the semi-group, a non-empty set G with binary operation star is said to be a semi-group if G comma star satisfies only closure law and associative law. We know already a closure law and associative law. When it is we take it down one note here. Just observe the guys. See, first one note is addition of natural numbers and multiplication of integers are the semi-groups because of addition of natural numbers satisfies the closure law as well as associative law, and multiplication of integers are the satisfy the closure law as well as associative law. That's why we called the first one addition of natural numbers and multiplication of integers are the semi-groups. Then second one point is addition of integers. The next one is addition of rational numbers, addition of real numbers, addition of complex numbers are all abelian groups because of these two. These four are satisfies the commutative law, that is A star B is equal to B star A for all a comma b belongs to G here. Now we know about the properties of groups. In that, first one property is the identity element in a group is unique. The identity element in a group is unique. Then second one property is in a group G comma star, the inverse of any element is unique. Yes, the inverse of any element is also here unique. Then third one is in a group G comma star, for all A belongs to a set G, this implies that A inverse of whole inverse is equal to, we get again A only. Then fourth one is in a group G comma star, for all A comma B is belongs to G, this implies that A star B whole inverse is equal to B inverse star A inverse. Then fifth one is in a group G comma star, for all A comma B is belongs to G, this implies that A star B whole inverse is equal to A inverse star B inverse. Then here G is an abelian. Then we go for sixth one property. If G comma star is a group and A, B, C is belongs to a set G, then in that first one A star B is equal to A star C. Then by using left cancellation law, okay, we get here B is equal to C only. Okay, here A get cancelled. By using left cancellation law, we get B is equal to C. Then we go for second one. Here B star A is equal to C star A. Okay, here by using right cancellation law. Okay, right cancellation law means, okay, we eliminate the right element. Okay, which one it is right element is A and A. We get the remaining element is, so B is equal to C here. Then we go for seventh one property. Seventh one property, that is if G comma star is a group and if A comma B is belongs to set Z, then the equations A star X is equal to B and Y star A is equal to B have the unique solutions in a set G. Unique solutions in a set G. Then we go for eighth one. If H is a subset of set Z, if H is a subset of set Z, then star is associative and commutative on H, on the set H. Then we go for ninth one. The inverse of identity element, yes, the inverse of identity element E is itself only. It means that inverse of E is E only. Then tenth one is star denotes the binary operations, that is addition, multiplication, dot is nothing but again multiplication, and subtraction. Last one is, yes, okay, these are the properties of groups. Now we know about the finite groups and infinite groups. In that first one, finite group, a group G is said to be finite if it is contains finite number of elements. When we called a finite group, a group G is said to be a finite if it is contains finite number of elements. Suppose if it contains n number of elements, then it is denoted as, O of Z. It is nothing but order of G, means order of group is equal to n. Okay, if group contains two elements, means order of, okay, group is two only here. So for example, okay, see here guys, okay, group G is equal to, so 1 comma minus 1 under multiplication, okay, is a square root of unity is group under multiplication, is group under multiplication. It means, okay, this group having only two elements, that's why we are taking square root here. The next one, second one is, okay, Z is equal to 1 comma w square, okay, under multiplication is cube root of unity group under multiplication, because of, okay, here, okay, three elements is there, that's why. So okay, we say that here cube root of unity. Then third one is 1 comma minus 1 I and minus I under multiplication is fourth root, because of, okay, again four elements here, so that's why it is called fourth root of unity. Fourth root of unity is group under multiplication. Then fourth one is 1 w square up to so on, okay, w raised to n minus 1 under multiplication is a nth root of unity is group under multiplication. Next one we go for the infinite group. Okay, we know already finite group now. So we go for the infinite group. A group is said to be infinite if it contains infinite number of elements. Yes, if it contains infinite number of elements, and order of group is also infinite. Order of group is also infinite. For example, so first one is a group of rational numbers minus 0 is a infinite group under multiplication. Again, next one is same, real numbers, then again complex numbers are also infinite groups under multiplication. Now we know about the addition modulo of m and multiplication modulo m. So that first one, addition modulo m. If m is belongs to a natural number n and a and b are any integers, then a addition modulo of b is written as, for all a comma b is belongs to integers, and a addition modulo m of b is equal to r, where r is less than m and greater than or equal to 0, and r is belongs to a natural number n. For example, if zm is equal to a set zm is equal to 0 1 2 3 up to so on m minus 1 is a finite abelian group with respect to addition modulo m. Then we go for multiplication modulo of m. If m is belongs to natural number and a comma b is belongs to integers, then multiplication modulo of a and b is given by a multiplication modulo m of b is equal to r, where r is less than m and greater than or equal to 0, and r is belongs to a natural number n. Definition of subgroup: a non-empty subset H of a group G is said to be subgroup of group G if H is a group under the same binary operation of G, that is, H satisfies the closure law, associative law, existence of identity, and also existence of inverse. In other words, okay, it can say that a non-empty subset H of a group, a non-empty subset H of a group G star is said to be subgroup of G if H star itself is a group. For example, okay, H is equal to 1 comma minus 1 under multiplication is a subgroup of G is equal to 1 minus 1 I minus I under multiplication. And second one example is here. Okay, integers is a subgroup of the, okay, rational numbers, and rational numbers is a subgroup of the real numbers, and real numbers is a group of complex numbers.